Good afternoon, everyone. Thank you for joining. We'll start with today's webinar. Good afternoon, Dr. Antanas. Hi. Yeah. So I will start with the introduction. So it's pleasure to introduce today's speaker, Dr. Antanas Urbas, Chief Scientist at Workshop of Photonics. Mr. Urbas holds PhD in physical chemistry and has decades of experience in research and development technology leadership at WOP. He leads research strategy and advises on partnership and innovation. His past roles include leadership positions at Lithium Space Association, 3D Center, and Alcatel-Lucent. With a strong background in photonics, laser application, and technology transfer, Dr. Urbas brings deep insights into precision manufacturing. So please join me in welcoming Dr. Antanas Urbas, and he presents on precise glass fabrication by selective laser etching, opportunities, challenges, and solutions. Welcome, Dr. Antanas Urbas.
Thank you. Thank you. And thank you all who joined this meeting. And to not disturb you with my face, I will switch off my camera to give more attention to what I'm supposed to tell you. So, as it was said, I would like to talk about opportunities, challenges, and solutions in selective laser etching, which is quite a powerful method of fabrication of glass, which takes off quite significantly in recent years, and we will see why it is so. Brief agenda. I would like to present who we are, Workshop of Photonics, what selective laser etching brings to the table, what is selectivity, what we can do by means of selective laser etching, why market demands it, and what influences results of your etching. Let me introduce ourselves very briefly. Workshop of Photonics is a small enterprise in Lithuania, small but smart. We are working 20 years in the field of laser micromachining. And in the last 10 or so years, we have the biggest focus on glass in our activities. We have patented some technologies I will present you later. And together with myself, more than 50 professionals are working together, 4 PhDs among them. The rest are mostly master or bachelor in physical sciences. And we also work closely together with academic and research partners around the world, starting from Australia and finishing with United Kingdom, just to be on the forefront of the investigations related to glass fabrication. Workshop of Photonics is a member of EPIC and Lithuanian Laser Association and Tools cluster in Lithuania, and we are also certified by ISO 9001. So, selective laser etching means precise fabricated glass. What it means precise? It is structures without chipping. No heat-induced stress, which means that after fabrication, your product will not break due to residual stresses. And you can make almost any shape in glass by selective laser etching, any form, any size, starting from 20 microns, sometimes even less. The surface you make, it is quite smooth. Roughness is below 1 micron. We will see how it looks like and what we can do to make it even better. And it is done in any form, meaning that if you may have tapered, non-tapered holes in your glass, so it is not like simple drilling. You can make whatever you want. And today, applications where this method is used, it's mostly microfluidic for producing chips and molds for plastic molding. Some guide plates for probe cards are also already made from glass. Carrier wafers are very often made from glass, and components for photonic chips, telecommunications, and related fields are also made from glass by means of selective laser etching. Recently, a very significant player stepped into the stage. It is Intel, who said that there's quite good idea to replace organic substrates which are used for making chips, to replace them with glass. And this is quite a big challenge because it is really mass production, but it is also demanding very high quality and very high profile features of the materials and products you're supposed to do. So why glass? So if you have a look at the main properties of the glass, we can see that we can select glass with coefficient of thermal expansion equal or very close to silicon, and there were special glasses developed which match very well silicon CTE. And what is important, that electric loss, signal loss in glass, each is significantly 2-3 times lower than in an organic substrate. Not speaking about tolerance for temperature, you can work with hundreds of the centigrade. You can make much more dense structures compared to organic substrates. And what is also very important, that you can seamlessly integrate optical interconnects into the chip, which is quite complicated if you use organic substrate. But if we talk about usage of glass and fabricating it with selective laser etching, it cannot be understood without understanding what glass is. I apologize for those who know a lot about glass, but I would like to emphasize some points to understand how this selectivity appears and what we do to get the selectivity better to make precise fabrications. So what is glass? It is, we can consider it as polymer built from the tetraedra with the formers, glass formers. You will see what it is in center of this tetraedra or on top. And sometimes you will see, when talking of glass, Q number, which defines how many links between tetraedra are in your chains or rings. So someone may ask what it means tetraedra. which means 4 oxygens to one former atom. After all, everybody knows that it is silicon O2. It is formula for silicon oxide. But if we see to the formula how the atoms are linked, so we can see that this polymer, this chain or ring, is built with bridging oxygens between silicon atoms. And if we consider that silicon is connected to 4 half of oxygens, meaning that only one bond of oxygen is linked to silicon, we come back to a really silicon O2 formula. So nothing no contradiction. Then next thing is which elements can build the glass. This is a very important table to understand which glass you can make. Blue marked are elements which have high valence state, which build covalent bonding with oxygen. And these can be, as I mentioned, centers of tetrahedra, which build chains which are bases of glass. And red marked elements, these are elements are used as network modifiers, which build ionic bonds with oxygen and modify the network, usually reduce glass network collectivity. And let's have a look how it happens. So if we have a chain of this silicon-based tetrahedra and add sodium oxide into the melt. So by the way, soda glasses are, I guess, oldest ones from Egypt. Sodium ion breaks the bond between oxygen and next silicon, just closing it and making it not bridging oxygen from this bridge. And the remaining radical of sodium O is connected to the next silicon, which means that you broke this chain, making it shorter. So meaning that you build more non-bridging oxygens and network connectivity is reduced. How different glasses are built? So if we take fused silica, which is built from a pure silicon tetrahedra, add some alkali oxide, as it was in previous example. So we will break some chains or rings inside of the glass. We may add, for instance, aluminum oxide, which may replace some tetrahedra, meaning that along with silicon tetrahedra, we will have aluminum tetrahedra. And you may add alkali earth oxide along with alkali oxide, which will block each of alkali earth elements will block 2. This meaning creating two non-bridging oxygens, and even more reducing network connectivity. So, and if we go to the real glasses, it is for 263T glass of shot. This is formed for 4 formers of glass: silicon, aluminum, boron, and titanium, and 3 network modifiers: sodium, magnesium, and zinc. So, and I can tell you that the more elements compose the glass, the more complicated becomes the process of fabrication, which is not surprising. So, what happens and what influences selective laser etching? As it is, as it sounds in the name of the process, it is two-step process. First of all, it is laser modifying, and then afterwards, modified material is removed by some etchant. What is important for this process? First of all, each type of glass requires approach. You cannot transfer what you made in borofloat to, let's say, Eagle XG, alkali-free alumosilicate. So again, it depends very much on what you want to achieve in your workpiece. Meaning that is it just cut? It is a free form hole. It is a blind hole, or whatever. And to match this type of glass and requirements, what you want to do in it, then you have influencing parameters like pulse duration, pulse repetition rate, scanning strategy, laser wavelength, and polarization. And after you made a modification, then the etchant steps in. Meaning you have to select proper etchants, you have to make etchant composition, which will be appropriately selective and efficient in the rate. Of course, you have to choose proper temperature and to control etching time. How the glass becomes selective to the etchant? So everybody knows that the glass is quite a good insulator, meaning that the gap between valence and conduction bands is roughly 8 to 9, sometimes even more electron volts, which means that you need 7, 8, 10 photons of 1 micron laser to move electron from valence band to connectivity band. And after you excited this electron, creating electron and hole pair, which is called exciton in the solid state physics, during 150 femtosecond, it is relaxing to self-trapped exciton, meaning that these excitons find locations on particular places in your lattice, which usually is accompanied with changing the angle of the bonds between these tetrahedra. And during next 100 to 400 picoseconds, which we will see as later as important time, color centers are built inside of glass. In this case, it's E center and the non-bridging oxygen hole center, where you have some hanging oxygen without binding anything, or tetrahedra with free bond at all. These are most popular defects which are created in the glass, and usually as a result of these defects, the glass is densified in this laser affected zone, which you can see as resulting in change of refractive index or appearing by refringence inside of glass. And more deeply, you can investigate it if you wish by checking with Raman or Express analysis. You can see how the bonds, non-bridging or bridging oxygens are distributed when before laser and after laser, which may somehow explain you how strong your modification is. So there was a list of lots of parameters which influence SLE as a process. So once we made this modification by laser light, then we can put various etchants to work. You can see that the fastest etch rate is in hydrofluoric acid, but the selectivity, meaning that difference between modified and non-modified material etching, is the lowest here. So it will be fastest, but you have to keep in mind that your workpiece will be thinned significantly as well while you etch your affected material. So if you want to be more selective, you choose you may choose alkali etching or ammonium fluoride, so which gives you more possibilities to be more flexible. Different glasses are also etched with different rates and different selectivity. So fused silica glass is most selective. You can see that modified and unmodified etch rate is can reach thousands, and it is almost 1 millimeter per hour can be etched in fused silica. If you go to borosilicate glass, like BF33, for instance, the etch rate is still high, not so high as in fused silica, but selectivity drops to hundreds, not thousands. And if you go to most popular these days, alkali-free boro-aluminosilicate glass, like, for instance, EGLG by Corning, selectivity is quite low, and the etch rate is also quite low. These numbers are measured with the same laser parameters and just varying etchants and concentration and temperatures, which give you this range, depending on concentration and temperature. So another important thing is etchant composition. One of the popular etchants which works fast is mixture of hydrofluoric and hydrochloric acids. So you can see that neither pure acid gives you the best result compared to some proper mixture of those. So omitting quite low selectivity of this mixture, if you want to have high etching rate, you can use HF plus H chlorine mixture with this proportion. So if we come back to this excited states which remain in the lattice after irradiation, you remember that it was some hundreds of picoseconds and later microseconds of excited states or colors which have significantly less absorption energy required to excite the material. So meaning that if you second laser pulse, like it is done in burst mode, it comes into excited glass prior to relaxation of these excited states, you can see that the etching rate becomes significantly higher. That all the remaining parameters equal, it can be some 10 times higher if you use double pulse, meaning you are exciting already excited glass states. So from laser point of view, it is burst mode versus non-burst mode, single pulse. So another important parameter, especially when you speak of alkali etching, is etching temperature and concentration. So you can see this hockey stick forms dependence of temperature after some 50-60 degrees centigrade of etchant solution. So it jumps 10 times or more compared to room temperature. So meaning that if you want to have fast etching in the alkali solution, you have to go to high temperatures. It is 100 and even more. And what is important for alkali etching that you have some optimal range of concentrations that which is between 30 and 35%. If you go higher, the etching rate drops again compared to this optimal zone. So, by the way, alkali etching, being quite selective, it is important to say that if you have these complex boron-alumo silicates, then you will meet the problems with removing the etching products where alumo silicates build non-soluble products which are hard to remove from narrow holes if you want to have narrow cuts. So this means that you have to use intermediate steps of washing away these products by acid solutions. So to make it more funny, this is so-called heat map for hydrofluoric acid. If we introduce polarization of the light, which modifies your glass, compared depending on pulse energy, or in one-dimensional or two-dimensional structures. So you can see that changing from circular polarization to perpendicular to scanning direction, you can have quite significant change in selectivity, which can reach 5 times or more. And the same is valid for alkali etching. As you can see, the same behavior is here, and most efficient, most selective etching is when you modify the glass with light polarized perpendicular to your scanning direction. So, how the fabrication started? This is one of the first examples how pictures were made in glass by means of selective laser etching. So here you can see example of focused laser pulse in glass, and if you scan these foci in one direction or in several directions, you can test how your etching works in your workpiece. So in this upper case, there were 11 lines of these foci scanned one above other, and just changing energy of single laser pulse showed that your shape can be somehow optimized by laser energy. And afterwards, if you access this threshold, it becomes not so nice. This is 2D example, meaning that you scan it in one direction and just to the depth. And if you make volume scanning, in this case it was 15 times 90 lines, 15 across and 90 into the depth, you can see that again you can find the optimal energy of the pulses you put in the glass to get nice and clean grooves in your workpiece. And this gentleman who made who presented this scientific paper, now they make quite sophisticated microfluidic chips by precise manipulation of beam shape and position. So, what is important to know if you use selective laser etching in glass? That your surface after the treatment will be not precisely smooth. So here you can see examples of hydrofluoric acid, mixture of hydrofluoric hydrochloric acid, and hydrofluoric and sulfuric acid. So you can see some bubble structure of micron size or submicron size, and the same you can see in our experiments where we used potassium hydroxide solution. So this is side wall of the via, or bottom of the cavity, which was etched away. So meaning that it doesn't matter which etchant you use, your surface resulting will be characterized by some bubbles on it. How to deal with this? So especially for microfluidics, when you make microfluidic cell, in many cases you need having optical quality in the analytic zone to deploy absorption, scattering, or luminescence methods of analysis. So meaning that your surface should be as smooth as possible. So here you can see standard smoothness of the SLE made microfluidic cell. And you can see that these paths we saw in previous slides, how you scan your focus in the glass, they remain. So some waviness is here, and along with this waviness, this surface is bubbled. This surface roughness around quarter of micron or even more. To have optical quality, you must apply some smoothening post-processing, which can be thermal post-processing. It is furnace or CO2 laser irradiation. And then again, you can see that this waviness caused by scanning stays, but these structures are much smoother. And in this case, we got surface roughness 60 nanometers, which was really satisfying these guys who asked us to make microfluidic cells. Again, checking what is how it is dependent on etchant. So we measured roughness inside of via etched by potassium hydroxide and fluoric acid. So we can see that peak to valley is approximately the same, 800 nanometers. So meaning that you will need the same post-processing, whatever etchant you use. So now let me price ourselves how precise we can be when applying this selective laser etching for glass fabrication. These are structures made from fused silica glass, meaning that we removed all the material which is in between these cones. These are approximately we can tell that it is sprayers using capillary forces to bring liquid through these channels in the cone. So you can see requirements, geometry requirements for these structures, that it was plus minus 1 degree cones, and these channels were were 10 micron wide and 4 micron deep, plus minus half a micron. So, and this was achieved across quite a big area, and it works, by the way. Glass precision internal. One of the products we produce is positioners for single mode fibers. Single mode fiber usually has a diameter of 125 micron, and the active core is 4 micron thick. So meaning that if you want to position the fiber to your photonic chip, your accuracy of positioning should be no worse than plus minus half a micron, and your precision of the dimensions of the hole should be also no worse than half a micron, because if it is less, if your hole is less, you simply will not push your fiber into the hole. So, and in the Workshop of Photonics, we make line arrays or 2D chips for aligning these fibers with region. So now we come to the buzzwords of the market, TGV, which means through glass vias. As I mentioned, Intel is pushing to go for glass core when making chips. So among other challenges, this one of the challenges is that you have to make up to 1.5 million holes in the 500 times 500 millimeters panel, which means that you have to make it fast. Again, it means, and this should be quite precise. These vias through glass should be, ideally, should be top and bottom should be equal. Actually, tolerance is 10%. The waste ratio to top should be, ideally should be 100%. Tolerable is 80%. Roundness 90%. Roughness 150 nanometers or so. So meaning that there's a quite big challenge to have these holes in this quite big panel, and all the holes should be same size and same form, because later they should be metallized, and if the form is different, the metallization process goes differently, and it is a problem. So what to do? So in previous examples, this was Gaussian beam used to make modification, to make volume modification, scanning in all three axes, X, Y, Z. But if you need to make 1 million holes, it will take days, if not months, if you use this Gaussian beam. So non-diffracting beam is a relevant tool to make it faster. And the bezel beam is simplest and most used for that purpose, which is made by conical lens, which forces superposition and interference of beamlets coming from different places of this conic lens, and you get non-diffracting beam zone quite long and quite narrow. So long story short, this diameter of the zone is smaller than you can get when focusing Gaussian beam, and as it is long, you can make modification with one pulse along all the thickness of your workpiece. So usually it is adjusted to thickness of the workpiece by using the 4F optical system, meaning that you have some hundreds of millimeters of tens of millimeters of the bezel zone. You reduce to the dimensions which are relevant to your workpiece, and you scan your non-diffracting beam inside of your workpiece. One quite important limitation is that these modifications cannot be too close to each other, because this modification will affect the next one because of shadowing, just closing the part of the light which should build this non-diffracting beam. So, what Workshop of Photonics has to say in this approach? We have patented the system which uses, as we call, special optical elements with inscribed birefringent structures into fused silica, which modify your beam, giving the shape distribution of energy and polarization inside of your non-diffracting zone. So here are a couple of examples of what you can do, making special patterns of this element which shapes your beam. So in this case, you will have non-diffracting beam having elongated cross-section in XY plane. More complicated. Sorry, I didn't mention the colors in these pictures mean orientation of fast axis of birefringent elements which are inscribed in the element. As you can see, this quite complicated element gives you several maxima on non-diffracting beam allocated next to each other, so we can call it optical knife. So you can use it for cutting free-form cuts using quite few pulses for long cuts. So, what can be done by means of this specific optical schemes? You can see here the TGVs we made in one of the glasses. If you, maybe it is a bit hard to see the numbers here. It is 600 micron thick glass, and 50 micron wide TGVs are made through this glass. And the difference between waist and opening is less than 10%. So we can say that optimizing laser beam shape and distribution, energy and polarization, combined with etching recipe, allows you achieving almost perfect TGVs. But what optimization means? So we can see that Here we can see results just changing duration of the pulse, and for each duration we change energy of the pulse. So you can see that the shortest pulse gives you quite wide range of the making TGVs, starting from a quite good waist to top ratio, and the longer pulses, 3 times longer. You can see that you need a lot of energy to make it work, and the waist will be very narrow. So meaning that the pulse duration has quite big influence on the via form. Again, what optimization means in terms of polarization pattern. As I mentioned, we change polarizations dilution in our non-diffracting zone. Here you can see examples what happens when you etch modified glass. Laser pulse and etching conditions were the same for all 3 examples. There were 3 different polarization patterns used. You can see that the diameter of the vias is almost doubled in sometimes, and the form is also quite significantly different. So meaning that you have very many instruments to play, but you have to know what you should expect when you made this or that. So let me come to some conclusions. So we can tell that this SLE process is defined by very many parameters. However, we can control it having some experience and knowing tendencies and trends. What happens if you know what is. For each purpose, you have to select proper laser and relevant etching recipe. Optimization is a long and painful process, and you never know if you reached a perfect solution or it is some local maximum. So, as a final conclusion is, if you want to start with that, you may start doing it yourself, but it will take a lot of time and efforts. And my advice is asking someone with experience for testing your concept and providing solution. So, if you have some question, please.
Hello. Anybody has any questions? I would like to thank Dr. Urbas for interesting and informative talk. Anybody has any questions? They can unmute themselves and ask.
Hi, Professor. I'm Anubhav from R&D unit Laser Science. So I have 2 questions. Am I audible, first of all?
Yeah. If you could make a little bit louder, it would be better.
Sure. So the first question is when usually a femtosecond pulse laser beam interacts with a glass, there are 2 reasons, right? You know, one, first, there is a refractive index change, and second, when we are there is a permanent structural change. So this type of SLE, that selective etching, which zone you choose for this etching? Is it the refractive index zone, where you have just interact the laser, and or where you have a permanent structural change?
You know, this refractive index change is also permanent. So meaning that
But
Usually
that doesn't
we
change
ask,
structurally much, right? I mean, if I
Yeah.
know clearly.
you know, these structural changes I was mentioning in my presentation, which lead to densifying
Exactly.
of the glass due to shortening of chains of polymers and changing the angles, bond angles. So these changes, these are permanent. So
Okay.
meaning that you can etch with the same efficiency today or tomorrow or in 2 weeks.
I see. Okay. And actually, I wanted to ask this tapering issue. I think you answered it in the end of the talk. Like you were suggesting to use hexagon, is it?
Could you say it again? I can hardly hear you.
Yeah. So actually, I want to know, like, when we do mostly this micromachining, we face the issue of tapering while removing the material. So that can be solved by using hexagons.
Yes, hexagon is one of the most popular element to build non-difference. But along with that, we modify this vessel beam, meaning that we use modified hexagons to have more sophisticated patterns of energy distribution and polarization distribution, which, as you saw, are both important.
Okay, would you like to elaborate? Actually, I wanted to know, like, say, when you say like hundreds of micron, if you like, without any beam tapering, so what type of hexagons are suitable?
Yeah, if you use plain hexagon, you can get 100 micron modification as well, depending on the energy you will put into the glass into this vessel zone.
Okay. One more thing, one of the slide you have showed, like there are some structures for fibers in the subsurface modification. So usually when we machine, like it's very difficult to achieve the circular holes. Can you suggest how you achieve it? Like usually the beam profile is like elliptical at the focus, right?
Yeah. You know, this ellipticity can be compensated by adding some elements which are shaped as Czernicke polynomials, and you may have some perfect round shape in the Z direction, and if you want to have elliptical elongation in our cutting direction, we make it with the ratios we want to have the best for the purpose.
Okay, sir. That's it from my end. Thank you.
Hello.
Thank you so much.
I have one
One more
question.
question we have.
Yeah, hi. Yeah, well, thank you. Thank you for this wonderful talk. Actually, so I just wanted to know actually how do you etch using the chemicals like potassium hydroxide and other things, and how they are different from the photoresist which we use in lithography as well. Their role.
You know, we use the same potassium hydroxide solution, which is used in many cases for photolithography or hydrofluoric acid. just without any photoresist on our workpieces. The selectivity is high enough to have the features etched only by difference of etching rates for modified and non-modified material.
So
The etchants are the same.
So you mean to say that before starting that micromachining, we need to put this what do you call developer or agent over that substrate, or we need to code PR something on over the substrate.
Sorry, can you say it again? I could hardly hear you.
So actually, my point is that as you mentioned KOS, right, like agent. So when we are going
Yes.
to use this agent before the micromachining or after the micromachining?
You mean KOH?
Yes, I mean agent. Yes, KOH.
Yeah, KOH etching is, I think, in our cases, in our experience, is most selective and very efficient for the glasses which have quite simple structure. If you have glass with lots of aluminum, then you will need. It is better to have HF etching or intermediate washing with acid.
So what we mean to say is that do you use these chemicals before applying the laser beam or after the
Only after.
After the laser beam? Okay, first you
Yes.
Micro machine it with the laser beam, then use the chemicals to etch it, to clean it actually.
Correct.
Okay, thank
First
you. That was nice to hear.
I have one short question.
Yeah, please.
Thank you for the nice talk. Can you go back to the slide where you showed bezel, this Hexicon with the 4F system? Hello?
This one?
No, back where you just introduced. Yeah, this one.
This one.
Next one. Next.
Yeah.
This one, yeah. So in the first image, I see immediately after Hexicon, there is a formation of bezel beam, and you are modifying the bezel beam by using some 4F system, right?
Yes.
So my question is, when you are using very high power laser, and there is won't there be any formation of plasma, the region where first bezel beam formation happens, which will eventually affect the final quality of beam due to plasma fluctuations?
Absolutely. But I must tell you that these are not high energy pulses which are used to modify the glass. These are hundreds of nanojoules up to hundreds of microjoules. So even with this tight focusing, it does not create any plasma.
Okay. Thank you.
Thank you for giving answer to all the questions, Dr. Urbas. Anybody has any questions? I think nobody has any questions.
So thank you.
Thank you, Dr. Urbas. Thank you, participants, for joining. See you in the next webinar in next month. Thank you so much for informative webinar. See you.
Thank you. See you next time.
Yeah. Bye-bye.
Bye.